Hi everyone, today I'm going to go through the teardown of the Schlage Connect BE469 door lock. So here we have the lock pretty much fully assembled except for the door. This one uses the Z-Wave technology, has no Wi-Fi interface, and it needs a Z-Wave hub such as Wink in order for it to be operated remotely. It can also be operated standalone through the keypad. One can add and remove codes, type in the code to unlock or lock the door. And of course, with the Z-Wave hub, you can have a mobile application where you can do all that stuff remotely, so it's very convenient. The main reason I wanted to do the teardown was to see whether I could add Wi-Fi capability to this lock. So here we have the lock in the lock position, and I'm going to use the Wink application to unlock the lock. Now we have the lock in the unlock position, and again I'm going to use the Wink app to lock the lock. So as you can see, I've removed the bolt and the keypad lock from the assembly, and I'm going to try to lock it, and because there's no limit, a stop limit, the lock doesn't work properly. Okay, now comes the fun part. So first of all, you have to remove this black cover here. Just pull it out. That's gonna give you access to the battery and battery connection right here. So make sure to undo this connection and then remove the battery pack. Next, you're going to remove this connection here, which is the connection to the keypad on the other side of the lock. So the next step is to remove these three Phillips screws. Once you do that, you'll be able to separate the metal case from this plastic piece. This plastic piece has a PCB on the other side, and if you flip this plastic piece to the other side, you'll be able to see the complete PCB. Now, in order to separate the PCB from the plastic piece, you have to push out these four black tabs as shown here. Okay, so this is as far as I went taking things apart. You can see here the DC motor. This is a little connector that connects the power coming from the battery and the motor itself to the PCB here. You can also see a set of gears that the motor drives, and this larger gear is, if you can see this little square here, this is where the bolt in the inside knob, door knob, is connected to. There's also a set of metal tips that make contact on the PC board. I'm not sure exactly what it does, but I believe that with the contacts on the PCB, the microcontroller is able to determine the position of the large gear and therefore the bolt. So now on to the more interesting part of this teardown. So as you can see, this is the PCB with most of the components. I believe all the components are on this side actually. This is a multi-layer board, at least 2 layers, maybe more, I'm not sure. So what I tried to do here was to break down this PCB into the different circuitries that make up this entire lock. This is where I was telling you about the square or the rectangular where the bolt attaches to. So on the other side, you have the indoor or inside doorknob. And this area here is where the larger gear makes contact to the PCB on the other side. And there's some indication here as to whether the lock has been interrupted, lock zone right, lock zone left, and whatnot. So somehow this communicates to the CPU here, the location, the position of the lock. But anyway, so here you have the connector that I mentioned before. This is where the motor and the battery connects to the PCB. This is the connector where the external keypad connects to the PCB. And here we have the buzzer driver. So I'll go into more details, but it basically increases the voltage for the buzzer, to drive the buzzer. You have the, this is just a little set of buttons and LEDs here for that inside button where you control the alarm and whatnot. This is the power regulator. It's an inline regulator, and again I'll go into more detail about that. This is what I call the battery circuitry. Essentially, among other things, it senses the battery voltage. You have the Z-wave circuitry. So this is pretty much a standard Z-wave circuitry that, you know, it's part of the Z-wave package. Here, of course, you have the buzzer. Here you have the CPU and the flash. So this is a microcontroller, and this is a serial flash chip. You have an accelerometer, so if you look at the spec of this lock, it will detect force applied to it and sound an alarm. And this is the H-bridge. So for me, trying to add Wi-Fi capability to this lock, this is what is the most relevant part for me. Before I go over the schematics of the power section of this block, I'd like to make a quick disclaimer. So most, if not all of these components were covered by conformal coating, and I had to buy a pen remover in order to remove the coating and be able to read the markings on the components. Unfortunately, they're all SMD, so the markings are so small, I ended up having to buy a magnifying glass, and I was not able to make out all the markings. So that's why you see places with question marks, which means that I was able to make out the H, the T, the P, the 2, although the 2 could be a Z, but not the rest. And some other components, you have the tilde, which means that I was not able to determine the exact part number of the component, but I was able to identify what I think is an equivalent. For the resistors and capacitors, for instance, I put the tilde in there to signify that those are measured values. Now that we got the disclaimer out of the way, let's go into the schematics. So the first component I want to point out is the battery pack itself. So this consists of 4 AA batteries, 6 volts when they're fully charged. And as I had mentioned before, the battery pack is connected to the PCB via a connector labeled J2. So pin 1 is connected to the plus, and pin 4 is connected to the minus. Next, you see here the power regulator section. which is pretty straightforward, except that, as you can see, the positive of the battery goes straight into the regulator, but the negative does not go straight into the ground. The reason for that is to protect the circuit from reverse polarity. So these batteries are placed by a user, so it is possible that they are placed in reverse. So in order to protect the circuit from reverse polarity, they added this N-channel MOSFET. So the simplest way to address that, to protect the circuit from reverse polarity, is to add a diode in line with either the positive or the negative of the batteries. The problem with that is the voltage drop across the diode, which is about 0.6 volts. So if you compare it to a fully charged battery, which is 6 volts, that means about 10%, and will get larger as the battery voltage drops. So there's also a possibility of using a Schottky diode. I'm not that familiar with it, but as I understand it, it has a lower voltage drop, but it's a little bit pricey, but still it's higher voltage drop than the MOSFET. So the way the designers of this lock decided for the MOSFET. So you have two choices. You can use a N-channel MOSFET like the one that they're using here, or you can use a P-channel MOSFET. If you use a P-channel MOSFET, you have to place it in line with the positive. And if you use a N-channel MOSFET like this one, you put in line with the negative. Now, the reason for the N-channel MOSFET is that the resistance between the source, the drain and source, is typically lower on the N-channel than it is on the P-channel. So I believe that's the reason they picked the N-channel MOSFET. And the way it works is very simple. Basically, when the battery is placed properly with the correct polarity, the voltage between gate and source, VGS, is pretty much the entire voltage across the lock load. So that turns the MOSFET on, and therefore this pretty much is the ground, connects to the ground. One key consideration when one is using the MOSFET is the fact that the MOSFET gate is connected directly to the battery, which is handled by a user. So there is a risk of ESD. So that's why they placed a voltage suppressor, a TVS diode, across to protect not only the MOSFET gate, but the rest of the circuit as well. Now, the rest of the circuit here is a linear voltage regulator. So there's a lot of discussions about using the linear voltage regulator versus a switching regulator, especially for devices that are very critical in regarding power consumption. They decided to use a regular voltage, linear voltage regulator. Again, here I was not able to make out the exact marking, but based on the package, which is SOT23, the pinout and the connections, I'm very confident that it is a type of MCP1702, and I measure the voltage to be 3 volts. The last portion of the power circuit is the voltage sensor. So typically you have a voltage divider consisting of 2 resistors, and then you measure the voltage and determine the voltage of the battery. However, if you leave this voltage divider connect between power and ground all time, that means you're burning energy the whole time. So what they did in order to save energy is they added a MOSFET here that operates like a switch. So the voltage divider is only connected to 6 volts to the power, to the plus, when the switch is on. And this switch is turned on by another MOSFET, which in turn is connected to a I/O pin on the PIC microcontroller U1. So essentially the way this works is that only when the microcontroller wants to read the voltage on the voltage divider, that's when this switch is turned on. And when the switch is turned on, the microcontroller reads the voltage right here. So this is pretty much it for the power section of the lock. So before I move on to the microcontroller in Flash, I want to make another disclaimer, which is the fact that, as you guys can see, just the microcontroller alone has 80 pins, and these are all very small devices. So I may be wrong in some of the pinouts that I've called out, for instance, on the power section before this, because what I did is I used a multimeter to do continuity tests. So it could be that I got the wrong pinout. Anyways, so this is the heart of this door lock. It's a PIC 18F87K22 microcontroller, which is designed for very low power applications such as battery powered devices. It's an 8-bit microprocessor running at 64 megahertz. It has 69 GIOs, generic IOs, 120 KB of internal flash, and 1 KB of EEPROM as AD converters, timers, and like I said, it's an 80 pin. Now, right next to it, you have here a serial flash that, again, it's a low power flash, 2 megabits, and uses SPI compatible interface. So I believe this is used to store user codes for the lock. If I'm not mistaken, one can store names and numbers, 4 to 6 digit pins to unlock the lock. So this is pretty much, like I said, the heart of this lock. So now on to the Z-Wave section of the lock. For those of you who do not know much about Z-Wave, Z-Wave is a proprietary software and hardware solution for very low power RF applications, such as some IoT applications. Sigma Designs bought the technology from Zenith in 2009. In 2018, Silicon Labs acquired the Z-Wave portfolio from Sigma, which went out of business. Now, Silicon Labs not only provides products based on Z-Wave, but also Zigbee, Wi-Fi, Bluetooth, and whatnot. So I'm personally not very bullish on the future of Z-Wave. Zigbee is a direct competitor of Z-Wave, where Z-Wave is a proprietary solution. Zigbee is open source, which is good and bad. The drawback is that there's so many different implementations for Zigbee that some of them are not compatible. In order to certify a device as Z-Wave, an OEM has to submit the Z-Wave device to a lab that's part of the Z-Wave Alliance, I believe, and it goes through a series of tests to make sure that's compatible. Since this lock uses the ZW0301 ASIC from Design Labs, it's considered a third generation Z-Wave product, which is based on the ZM3102 module. So to have an idea, this is the ZM3102 ZM3102 module right here. So it's very small. It has the ASIC here, which is the ZW0301. It has an oscillating crystal and some additional components. And it has another chip. This is U3 on the Lux PCB. I was not able to determine what it is for sure, but my bet is that it is an SAW filter. So here we have a depiction of what this module is. So the ZM3102, it basically contains the chip itself, the 0301, which is the brains. It uses a 8051 core. It has an internal flash, RAM, and I/O ports and whatnot. And it has a oscillating crystal. It has the RF front end, which I believe includes the SAW filter and some other small parts. So the manufacturer of this lot could have bought this module and added to the PCB, but instead they decided to take these parts and add them directly to the PCB, probably because they have a high unit volume anyways. The Z-Wave chips are now on their 7th generation, and they no longer are based on the 8051. Instead, they use an ARM microcontroller. So the designers of this lot decided to use a PIC microcontroller to run everything else they needed inside the lock, probably because of the limitations of 8051 core. Now, if they were to design a new lock based on the 7th generation of Z-Wave chips, they may decide to use the ARM microcontroller for everything else they need. So this chip, U7, was a bit of a mystery for me. First of all, I was not able to read the entire marking on the chip. I was able to make out the 8524, but not the rest. And I researched everywhere for a chip that had these numbers I couldn't find anywhere. So this was a chip that was sitting sort of by itself in the middle of the PCB. The first clue I had was that there was a Y and X labels on the PCB itself. So that led me to believe that this was perhaps an accelerometer. If you look at the specs of this lock, you'll find that it does detect attempted forced entries. So again, a sign that it has an accelerometer. So I went with the idea that it is an accelerometer. Another interesting or peculiarity of this chip is that it has 16 pins. And instead of having a 4x4, 4 on each side of the chip, 4 pins on each side, it actually had 3 on one side and 5 on the other, and then again 3 and 5. So that was kind of unique. So assuming that this was an accelerometer, and then I traced the connections to the rest of the board like this, and I started looking for accelerometers that would be at least 2 axes, perhaps 3, had a pinout that matched this, had a unique pinout configuration of 3x5. So the best match I found was this one here. So this is a 3-axis accelerometer, ultra low power, high performance, and uses SPI as interface. The buzzer seems to be controlled by the circuit right here. Although the label on the PCB implies that this is a transformer, it was T1, I wasn't very sure. So I've disconnected one of the leads from the PCB and measured the resistance between the leads to make sure they were not just taps from the same winding. I don't own an LCR, but based on the resistances, the TR is probably 1 to zero point 0.1. I know it's not very accurate, but it's an indication that it is a step-up transformer. To be honest, I'm not sure how this driver works, but I believe this 7 here works as a reverse polarity protection, and this being a step-up transformer, so when this MOSFET is turned on by the PIC microcontroller, you're basically going to have 6 volts going across the primary of the transformer, and assuming that the ratio is about 10, so you may end up having like close to 60 volts here in series with the 6 volts, so you could be around 66 volts across the buzzer. I actually had the alarm go off on me accidentally, and it was pretty loud. So we finally get to the last section of this block, which for me is the most relevant one, as my goal is to add Wi-Fi capability to this lock using, say, an ESP8266 module and manually control the motor. The first component is the motor itself, which is connected to the board via the J2 connector, which is the same connector used to connect the battery. This lock uses the DRV8833 motor driver, which is a full dual H-bridge motor driver. And the designers decided to parallel the 2 outputs, the 2 H drives, to control one single motor. As you can see on this table, these inputs here, which are here, are controlled by the PIC microcontroller, and basically, depending on their values, it dictates whether the motor spins forward or reverse, meaning either opens the lock or closes the lock. As you can see, this driver also has a sleep mode in order to save energy that is controlled by the PIC microcontroller. It also has a fault output, which is active low. I was not able to find where it connects, so it may not connect to anything. It may not just be used. Well, we have finally come to the end of this teardown. I hope you have enjoyed and learned a few things. If you're interested, I've added some links in the description section for some of the tools used to perform this teardown. In my next video, I'll try to operate the motor by manually driving the H-bridge directly. That is, bypassing the Z-Wave hub and the PIC microcontroller altogether. If you like this video, please hit the thumbs up and subscribe buttons. Thank you very much.